Right, lastly, we look at the exponential function. And the key identifier here is that the input is in the exponent. So this number over here, number 2, is just a number that I've randomly chosen. And in fact, we're going to look at what playing around with this number, how it affects the graph, or how the graph of the corresponding graph of the function looks. So let's start out by thinking about this guy over here. Y is equal to 2 to the x. So whatever your input is, you take 2 and you raise it to the power of that input. So for example, when my input is 1, all right, then I'm going to have 2 to the power of 1, which would just be 2. So my output would be 2, and so that's the first point I can plot there. When my input is 1, my output is going to be 2. And then likewise now, if we're to increase our input a bit, so let's say we take it up to 2, so then I've got 2 to the power of 2, which is 4. So my output is 4. That's the next point that I plot. So my input is 2, my output is going to be 4, right? And then if I change my input to 3, so I'm going to have 2 to the power of 3, which is not 6, it is 8. So your output there would be 8. So that's the next point that we plot. When my input is 3, my output is going to be 8. So there are my 3 points over there. And those 3 points don't really give me a sense of the shape of the graph. So I'm going to look at some inputs going in this direction. Starting with 0. So what happens when the input to my function is 0? Well, 2 to the power of 0, by definition, anything to the power of 0, except for 0, is just 1. So my output would be 1. And so that would be my next point. When my input is 0, my output is 1. And so there goes my point there. Then life gets a bit interesting if we consider negative input. So this is where you need to dig back into your knowledge of exponents. If my input is -1, I've got 2 to the -1. And remember that a negative exponent allows you to move a power across the fraction bar. So 2 to the -1 is just the same as 1 over 2 to the +1, otherwise known as a half. So, I don't know if I can get some precision here, but I'm going to do my best. So when my input is -1, my output is going to be somewhere between 0 and 1. So let's try and get that. Oh, I'm so nervous. Okay, that's my best effort. Yeah, it looks like I kind of almost got it. Anyway, and then likewise, so sorry, got to do the grand reveal there. And if my input is -2, again, by a similar process of reasoning, you end up with your output being a quarter, or 0.25 as a decimal. So this is going to be even harder to plot. Oh my gosh. Let's see if I can zoom in a bit and to try and get that almost precise. So 0.25 needs to be somewhere between 0 and 0.5. So that's, well, not somewhere between, exactly between them. So when my input is -2, my output is going to be, let's say over there. Alrighties, let's zoom back out. Okay. Wow, some of my stuff disappeared. Oh no. Okay, so there's a point that went MIA. There was that point way up there. Anyway, that's fine. We can live. And then if we're to be even sillier and make our input even smaller, okay, sorry, let's just move this back in. Cool. So let's say we make our input -3, okay? Then my output is going to be an 8, right? 2 to the -3 is 1 over 8, which is 0,125. And that would be somewhere over here. I'm not even going to try and plot that. But the trend, as you can see, is that the smaller I make my input, the smaller that output is going to be. The closer and closer to 0 it's going to get. And this is what the graph of this function looks like. So there we have it. And you'll see that over here, it looks like the graph is eventually touching the y-axis, which implies that at some point, when your inputs are small enough, your outputs are going to be 0. That is not the case. So if we zoom in a bit here to see what's going on, the finer we make our zoom, we'll see that the graph is not actually touching the y-axis. It's just that these values are so incredibly tiny, 2 to the power of -7.6. If you try and work that out on your calculator, you're going to get a very small number. And so it goes. So the y-axis is actually an asymptote for this function. Not the y-axis, sorry, that was a trick. X-axis. The x-axis is an asymptote for this function because at no point is there going to be an input that makes 2 to the power of x equal to 0. And that's an important feature of the exponential function, well, the basic exponential function to remember. Right, and then as promised, the question that we want to ask ourselves is, that was not intentional, what happens when we modify this number, the base of the power? And what we saw was that if we make this number larger and larger, so if it's some number bigger than 1, the more you increase this number, the steeper your graph is going to be. So, for example, we're going to keep a copy of the graph of this function y is equal to 2 to the x as a point of reference. So you'll see it's over there behind the blue line. It's dotted. And this is the one where we're going to play around with the base of the power. And you'll see that if we're to increase it to 3, for example, so if we'll look at it in two parts. Over here on the right-hand side of the x-axis, you see that this y is equal to 3 to the x has bigger outputs for the corresponding inputs on this function, right? So, for example, when the input is 1, y is equal to 2 to the x just gives us 2, whereas this one gives us 3. And when the input is 2, y is equal to 2 to the x gives us 4 as an output, whereas this guy you can't even see, but the output would be 9, so somewhere up here. And so it goes. So over here on the right-hand side of the input axis, so to say, you have a much steeper curve because the outputs are bigger. Whereas on this side, you find the graph of y is equal to 3 to the x going underneath the graph of y is equal to 2 to the x. And maybe pause to think to yourself why that is. But yeah, it's the idea that, the same thing that worked for y is equal to 3 to the x on this side works against it on this side. Because 3 is a bigger number, when you move it to the denominator of a fraction using a negative exponent, that means you get a smaller fraction. So, for example, when my input is -1, the output of this function is just going to be a half, whereas this one would be a third, which is smaller than a half. And likewise, when your input is -2, the output here would be a quarter, whereas over here it would be a ninth, and a ninth is smaller than a quarter. And so it goes. So that's how playing around with the base affects the shape of the graph. And as you can imagine, if I make it even bigger, you see that steepening on the right even more acutely, and then just that departure over here on the left hand side is also larger. The y is equal to this guy is going to give us much smaller output on this side, whereas on this side it's going to give us much bigger output. And so, yeah, we can see that the base has a steepening effect. And then another interesting case to consider is, we've looked at when the base is a number bigger than 1. What happens when you have a number between 0 and 1? So here's the graph, for example, of y is equal to a half to the power of x. It looks like that as compared to this guy. Y is equal to 2 to the x. And the reason it looks that way, I think it's easier to explore it first looking on this side of the input and then looking on the left-hand side. So a half to the power of x, the bigger you make this input, the smaller the output is going to be. So over here, for example, you've got, obviously a half to the 0 is going to give you 1. A half to the power of 1 is going to be a half, and we can see that indeed it's halfway between 0 and 1. And then a half to the power of 2, remember, is a half times a half. So you're halving a half, you're going to get a small number, right? You get a quarter. And if you say a half to the power of 3, well, then you're saying a half times a half times a half. You're going to get an even smaller number. And so it goes. If you say a half to the 4, you're going to get a half of a half of a half of a half. And so, the higher your input is, the more your output approaches 0. And once again, like the zooming we did earlier in this video, we'll see that it doesn't actually ever touch the x-axis. It's just that the output becomes very, very tiny, very, very close to 0. But it's never actually going to be 0. So that explains this side of the exponential graph when this guy over here is a proper fraction. And it's important to stress that this is only applicable when this base is a fraction between 0 and 1. If this was something like 1.5, then the bigger you make this input, then the larger and larger your output would be. 1.5 times 1.5 is going to be a bigger number, times another 1.5, etc. So that's why when we talk about this case, we don't just talk about the case of it being a fraction, because it's not just about it being any fraction, it's specifically about it being a fraction between 0 and 1. A fraction that, the more you compound it, the smaller and smaller the output is going to be, type of a thing. And if we look on this side of the graph, what's happening is that these negative inputs are making this exponent negative, and that negative exponent allows you to move. For example, a half to the power of -1 would be the same as, right, always better to write things out. So a half to the -1, we know that the laws of exponents tell us that we're allowed then to rewrite a half to the -1 as 1 to the -1 over 2 to the -1. And because both these powers have a negative exponent, it allows us to move this guy to the top, allows this guy to come to the bottom, and so we end up with 2 to the 1 over 1 to the 1, and that simplifies to 2. And so you end up with a half to the -1 giving you 2. And if you're to look at the input being -2 instead, then you end up with 1 to the -2 over 2 to the -2. And the 1 really doesn't do much because 1 to the power of anything is just 1. So the big deal breaker here is this 2 over here. That's what's really having a big impact here. And you end up with a 4 over there. So when your input is -2, your output is +4. And you can imagine that if you were to change that to a 3, that 2 to the power of 3 ultimately becomes a 2 to the power of 3. It ends up giving us a very high output. And the more you go this way, the higher that output is going to be, because that negative exponent is giving the 2 license to move to the top and make a very big number. So that explains the shape. Why is it a decreasing graph? when there's a proper fraction here at the base.